In this video, I prove the law of quadratic reciprocity. So I recall what it is. So I take two distinct odd primes, and then the product of the Legendre symbols, PQ, QP, is -1 if P and Q are both congruent to -1 modulo 4, and otherwise the product is 1. This is what I will prove in this video. So to prove that, I work on the following ring. So I take the polynomial ring on Z over QZ, and I quotient by the ideal generated by 1 plus x squared plus xp minus 1. So in this ring, an element can be represented by a polynomial of degree at most p minus 2. And the representation is unique because if we have two representations by polynomials of degree at most p minus 2, then the difference would be a representation of 0. But then 0 would be represented by a polynomial of degree at most p minus 2. But then in the polynomial ring, z over qz of x, the polynomial representing 0 would be a multiple of 1 plus x squared plus xp minus 1. And this is not possible. So we have a unique representation. So we work on a ring where we have a piece root of unity because 1 minus x to the p is 1 minus x times 1 plus x squared plus xp minus 1. And the second factor is 0 in the ring. And then x to the p is equal to 1. So I can talk about x to a power in z over pz because if I choose k in z over pz and I take a representant of this class modulo p given by r, then x to the r does not depend on the choice of the representant. So if k represents, if r represents k, then x to the r does not depend on r in the class k modulo p. So we can define x to the k without ambiguity. So I start by considering the Gauss sum. This depends on a and p. So it's the sum of x to the a k squared. So what can I say about this Gauss sum? First, I can look at the values of k squared. So if I list the values of k to the k squared in z over pz, so what do I get? I get once the value 0, 0 squared equals 0, twice each non-zero quadratic residue modulo p, because if I get k squared equals some quadratic residue, then minus k to the square is also the same quadratic residue, so I get it twice. And the non-residues, I don't get them. So I get 0 times, once 0, twice the quadratic residues, and 0 times the quadratic non-residues. So I can summarize this by saying that a value m in z over pz appears 1 plus Legendre symbol mp times. If the Legendre symbol is 1, it's quadratic residue, it's twice. 1 plus 1 is 2, and 0 for 0, the Legendre symbol, and minus 1 for the quadratic non-residues, and then 1 plus minus 1, 0 times. So I can summarize the number of times each value appears as a square. So because of that, I can write my Gauss sum as sum of 1 plus Legendre mp times x to the am. But the sum of x to the am is equal to 0 because am, if a is non-zero modulo p, the values of am runs over all values of m. So because the multiplication by a is a bijection of z over pz, and then the sum of x to the am is equal to the sum of x to the m. And then this is 0 because in the ring z over qz of x quotiented by 1 plus x to the p minus 1. 1 plus x plus x to the p minus 1 is equal to 0. So the sum of x to the am is 0. And then I can subtract the 1 in the bottom line, and I get another expression for my Gauss sum of Legendre MP x to the am. So I can also consider the inverse of a modulo p, and then I do a change of variable, which is bijective, n equals ma. And what do I get in this case? I get sum of a minus 1 n p times x to the n. And then I can factor, because the Legendre symbol is multiplicative, so I can factor the Legendre a minus 1p, and then I get a minus 1p times sum of np x to the n. But a minus 1p and ap are equal, because the ratio is a square p, and a square is the square modulo p. So the Legendre a minus 1p is the same as ap. So I get g of ap is Legendre ap times g of 1p. Okay, so this is very classical relationship between Gauss sums. Another classical relationship, but a little less simple, is the computation of the square of the Gauss sum. So I compute the square of g1p. So first I write the first factor g1p as g minus 1p times Legendre minus 1p. And then I factor the Legendre minus 1p. And I expand my Gauss sums. And then I write the sum as a sum on KL in Z over PZ of x to the k minus L times k plus L. And now, from Ka, I do a change of variable BC equals k plus L, k minus L. And this change of variable is bijective because there is an explicit reversed bijection. It's just two equations with two unknowns. And because P is odd, 2 is invertible, so I can reverse my change of variable. So this is a bijective change of variable. And if I apply this change of variable, I get square of the Gauss sum is Legendre minus 1p times the sum of x to the bc for bc in z over pz. So now I compute this sum by taking different values of b. So if I fix b different from 0, and I sum on c, then I get a sum equal to 0 because the multiplication by b is bijective. So sum of x to the bc is sum of x to the m, and again it's 0. And if b equals 0, the x to the bc is just 1, so I sum 1 for all values of c, and there are p values, so p terms in the sum, and then the sum is p. So if I sum everything, I get that the square of my Gauss sum is a prefactor Legendre minus 1p times p. So I get this nice formula, which is also very classical. And now what do I do to get this quadratic reciprocity? I raise my square of the Gauss sum, I raise it to the power q minus 1 over 2, so which gives Gauss sum to the q minus 1, and then I multiply again by the Gauss sum. So I get in total Gauss sum to the power q, and then so I raise to the power q minus 1 over 2, so I get Legendre minus 1p to the q minus 1 over 2 times p to the q minus 1 over 2 times the last factor, Gauss sum 1p. So I get this equality. But now, if you remember, we are in the ring z over qz of x divided by some polynomials. So the coefficients are taken always modulo q, the coefficients of the polynomials. So I can reduce modulo q and apply Euler criterion. So Euler criterion, the minus 1 Legendre p is minus 1 to the p minus 1 over 2. And p to the q minus 1 over 2 is the Legendre symbol of p and q. So I get, in fact, Gauss sum to the power q equals Gauss sum times -1 to the p minus 1 q minus 1 over 4 times Legendre pq. So I get this equality. Now I will compute the q's power of the Gauss sum in another way. And I will compute it by a direct expansion. So I just expand my power q of my Gauss sum, and I apply multinomial theorem. So I get a big sum of different powers of x times some coefficients. But what happens is that all the multinomial coefficients are divisible by q, except when we take the q's power of a single term. Because except if R0 or R1 or Rp minus 1 is equal to q, otherwise we have q factorial divided by smaller factorials, and then I get a factor of q at the numerator and no factor of q at the denominator. So since q is prime, the ratio is divisible by q. So all multinomial coefficients are multiple of q, except when one of the rk's is q and the others are 0. All the other coefficients are multiple of q. So what happens is when we reduce modulo q, because we work on a ring where we reduce the coefficients modulo q, we get that the q's power of the Gauss sum is in fact just the sum of x to the q k square. And then it's the Gauss sum qp. And then it's Legendre qp times the Gauss sum g1p. So I get this equality. So in fact, I have two expressions for my q's power of the Gauss sum, this one and this one. And then if I compare the two and I make the difference, I get 0. And this gives g1p times what is in the bracket equals 0. Now I can multiply by g1p, the left-hand side, and then I get g1p to the square, but this has been already computed before. And with the previous computation, we get Legendre minus 1p times something in the bracket equals 0. So now everything works in the ring z over qz quotiented by 1 plus x to the p minus 1. But here, the left-hand side is represented by a constant, just some coefficient in z over qz. But we have seen that there is a unique representant of any element of the ring we are working on. There is a unique representant of degree p minus 2 or less. So because of that, if we are represented by a constant, there is only one possible constant, and then if the element is equal to 0, the constant is equal to 0. So it means that necessarily the left-hand side should be 0 in z over qz. So now p is different from q and prime, so this is coprime with q. So the prefactor is invertible in z over qz. And then the bracket should be equal to 0. And then modulo q, I get an equality. And then this equality, in fact, it's an equality of Legendre symbols, so it's symbols which are minus 1 or 1. So in fact, it's an equality in z. And this equality is exactly equivalent to the quadratic reciprocity.